Welcome to class. In this video, we are going to learn how to solve differential equations using the Laplace transform. Let's get started. The reason Laplace transforms are so powerful for solving differential equations is that they turn differential equations into algebraic ones. Through this theorem, if I have an n times continuously differentiable function that's defined from 0 forward, that means I can take its Laplace transform, and its nth derivative should exist. The nth derivative is transformed into this big algebraic expression, where I get s to the n times the transform of the function f to begin with. And then I subtract derivatives of the original function evaluated at 0 times s to decreasing powers as derivatives go up. And this looks like a super arbitrary formula. I want to show you at least where the n equals 1 case comes from, and you should be able to see that the argument continues for higher order derivatives. So let's look at the derivative, at the first order derivative, at transforming that. Well, the definition of the Laplace transform is the integral from 0 to infinity e to the negative st times my function I'm transforming, f prime, dt. And what I'm actually going to do from here is I'm going to use integration by parts, where I'm going to let this guy be u and this guy be v. And what I get is u times v, the antiderivative of f prime of t dt, well, that's just f, evaluated from 0 to infinity, that's with respect to t, minus the integral of v, which we just said is f, this is, of course, from 0 to infinity as well, times du, which is negative s e to the negative st dt. Evaluating this limit, and I'm doing some hand waving here, by the way, I see that this exponential term will take it to 0, subtract, plug in 0, I get 1 times f of 0. So there's negative f of 0. And then over here on the right-hand side, if I factor out that s term, so I will get a negative negative, so plus s times the integral from 0 to infinity, e to the negative st, f of t, dt. What is that? That's the Laplace transform. So I got s times f of s minus f of 0. And there's that first order case done. How do we use these to solve differential equations? Well, I've got a simple one up here, and in fact, this is one that we learned how to do way toward the beginning of this class. We can even do this just through a simple integrating factor. And applying my initial condition, we know that we should get y of t equals e to the t minus 1. But I want to verify that we can get the same solution using the Laplace transform, just to give you a bit of faith that it works, because it feels a bit like magic. Okay, so let's see if we can get it with the Laplace transform. The idea is we want to transform both sides of the equation. That is, we want to take the Laplace transform of dy dx minus y equals the Laplace transform of 1. Now, I can use all those wonderful properties of Laplace transforms to break this up a little bit. I'm going to use the linearity to split this as dy dx minus transform of y equals, well, I actually know the transform of 1, it's 1 over s. Now, the goal here is that I do not know what y is, so I don't know what the transform of y is. But if I could find the transform of y, I can use the inverse transform to get y. So that said, I'm trying to isolate the transform of y. I can use that property of derivatives that we just looked at to write this term as it's the first derivative, so I get s times the transform of the function minus the function evaluated at 0. But wouldn't you know it, I know what y of 0 is. It's one of my initial conditions. It's 0. So factoring out the Laplace transform of y and then dividing the remaining s minus 1 over, I get that this is 1 over s times s minus 1. And now, in one more logical step, I get that y is the inverse transform of 1 over s times s minus 1, which we actually did together in a previous example. It's e to the t minus 1.